Let's continue with this topic. I think this was the last slide that we did with in the previous class. In relation to reservoir simulation, what they are, or reservoir simulators, what they are. We use reservoir simulation basically for modeling the dynamic behavior of a reservoir. They are numerical models of reservoir combining the reservoir properties, static properties, with physical principles that are expressed in terms of mathematical equations in order to describe the behavior of the conduit or the fluid that is involved in this analysis, gas, oil, and even water. Basically, like a unified system, integral system. Static properties and dynamic properties. It's functional because it gives life to the reservoir. And the life of a reservoir for us that we are in this business is the production. We need to know about production. Okay? So they are basically, this model used for performance forecasting, as I say here, and we are combining several physical principles and analytical methods. In a sense, we can say that we are basing on three-state equations: energy, momentum, and mass. Conservation of mass, conservation of energy, and conservation of momentum. And that can be translated simply like material balance, the fluid flow mechanics, the logical process, and pipelines and facility networks. Okay? Basically, they allow the design of reservoir exploitation schemes. Application, just for mention a few. We can go deeper in this list. Reservoir management, recovery prediction, process design, strategic planning, testing impacts of reservoir parameters whose values are uncertain, what-if scenarios, analysis of complex reservoirs or complex process, risk analysis and decision making. The idea here is, let me use a model to speculate about performance. That's it. You can even design an exploitation plan of your reservoir based in simulation. Stick it. You can try to figure out if the process of CO2 injection can be successful or not, just using simulation. You can even combine the reservoir simulation with statistical distributions in order to get probabilistic approach of the production. It can be done many things in reservoir simulation. It's a, as I said before, it's a passionate topic, a subject. Basically, the approach of a reservoir simulation is deterministic. You provide the input, you have the black box, and then you get your output. Basically, it's deterministic. However, can be introducing a probabilistic context if we introduce process like Monte Carlo simulation in order to represent some of the parameters of your inputs in the reservoir. Given some inputs, reservoir grid model, fluid description, well locations and completion process, production and injection information if you have it, initial condition for pressure and fluid saturation. All this information needs to be provided when you deal with reservoir simulation, and more if that's the case. And we talk later about black oil and thermal simulators, etc. But depending on the process that you want to model, you will need more or less or more specific kind of information. In order to get what? Well, the reservoir simulator predicts, as a function of the time, grid block pressures, okay? Grid block phase saturation, fluid compositions, if that's the case, and well performance, in a sense. In a sense, we are dealing with the performance of the reservoir based on well performance, okay? In order to do that, we need to represent what is the reservoir. If we have wells, if we have production, if we have pressure, if we have saturation, if we have information of the reservoir, we need to use it and provide it in order to get the reservoir simulator working as the objective that this simulator had. Some major simulation characteristics. Okay? Well, it's a physics model of fluid flow. So we have a very sophisticated physics and mathematics representing what is happening in a reservoir. It's well understood and it's been established in a while. Okay? PVT need to be set up, need to be established. PVT, we all know that. Pressure, volume, temperature. We are going to deal with temperature according to the kind of process that we are analyzing. We can assume constant temperature, but it is probably a simplification of the model. We need to provide, essentially, the characterization of the property of the reservoir. It's what I have called parallel rock property, from the vertical point of view and from the aerial point of view. And then we provide detailed calculation at each grid cell. Okay? These calculations are not assuming that we are providing average value to the whole reservoir. We are not thinking the whole reservoir like a tank, basically that. We are, in any case, we could be conceiving every single grid cell like a small tank. That's probably the key here in detailed calculation. Every single grid cell can be conceived as a small tank, and they are connected. We need also to figure out how to solve or how to describe the connection, because fluids are flowing through them. And fundamentally, the Darcy law is what is describing the flow through phases and boundaries of every single grid cell. Major simulation components. Well, just to simplify things and to get an idea about what's going on here, we need to deal with the discretization of the reservoir. In other words, we need to provide a characterization of splitting my reservoir in grid cells that cover or at least try to represent my whole space. Models are composed of discretized tanks, I mentioned before. We are conceiving every single grid cell like small tanks. Okay? Material balance is present every time. Okay? Each time obeys the rule of material balance. I suppose that I'm not dealing with matter that you don't know at that moment, right? Material balance, PVT, all this stuff you have studied before, in other course, right? Okay. Darcy law, these tanks, as I said before, they communicate. We are dealing with flow through them, and they have phases of common. And one tank, small tank, contribute to other, either with flow, either with the pressure, etc., etc. So think that we need to interconnect all these tanks in order to represent what is happening there. And the representation of the wells, well, we propose the location of the well as being covered also for grid cells. Wells are placed in cells at well location. Okay? Major simulation components. Fundamental, two types of discretization. Discretization space, discretization time. Why? What is this? I have said before, and you know also from other courses, that we are representing the behavior of the performance of the fluid with some equations. Based in the physics that we are analyzing, we represent the physics, well understood, okay, in terms of mathematical equations. Most of these equations cannot be solved from the analytical point of view. And because of that, we need to use numerical methods. Numerical methods need to discretize the domain, the space domain, and the time domain. Do you understand the terms space domain and time domain? Domain. Do you remember calculus 1, the domain of a function? Where is the function defined? Remember, I am using with the same meaning. When I say space domain, is the space where the reservoir is defined. When I say time domain, I'm telling the time that you are considering the performance of the reservoir. Okay? When we propose a grid for characterize my reservoir, we are discretizing my space. Every proposal that you do for gridding your reservoir implies automatically a discretization of the reservoir in small parts. What is the opposite of discretization? Completely continuous. Let me explain probably better in time. Okay? When we decide the time, we are not measuring every single nanosecond of the performance of the reservoir, right? We analyze probably every day, every hour, every week, every 2 days, every 3 days. We do some jumps, right, in the time. We are breaking the continuity of the variable time. You follow me there? That's exactly the process of discretization. Instead of analyzing every single nanosecond between 0, my initial time, and a month, we just propose every 2 days. So what is happening every 2 days is giving an idea about the performance. We don't need to go continuously for the variable that we are analyzing. Because of that, we need to deal with simplification of my problem. Now imagine extrapolate this idea to space. A reservoir is a continuous. Instead of the continuum in time, it's a continuum in space. Every single point to every direction is a continuum. When I do and move my hands, I am touching everything. This space is a continuum. But when we propose the characterization grid, we discretize on small cells that give you this partition of the space domain. After the philosophical dissertation about discretization, let me deal directly with some more realistic terms for you in terms of petroleum engineering. Spatial discretization. An entire reservoir is divided into many grid blocks. Okay? The grid cell properties, the heterogeneity of the reservoir must be averaged to represent what is happening in these small homogeneous blocks. Okay? Measure in feet or meters to hundreds or thousands of feet or meters. You go from the scale that you want proposed. You can go very fine, and you can go coarse. It's just minor decision. Based on what? Well, the kind of problem that you are addressing. Maybe you can go coarse. Maybe you need to be refining. Typically, we refine around wells because we are interested in represent what is happening there, either with inputs or with outputs. What about time discretization? Well, these time steps are proposed. As I said before, I can go jumping the time. Every day, every 2 days, every week, every month. When production rate is provided, usually it's daily. They are not giving you every single second about the production rate. Usually it's daily, a kind of rate daily. Even more, that you average in order to provide the monthly production rate. And usually we analyze monthly production rate in order to use decline analysis and curve types, type curves, hyperbolic and exponential, etc. Transient properties, they don't change during these time steps. If I say that I am adopting every 2 days my time step, it's a value representing what happened in these 2 days, period. You don't have half day, you don't have 3 hours, you just have these 2 days is happening something related with this particular block. And the dynamic properties are calculated only on these exactly time steps. So we are dealing with two different discretizations, so space domain and time domain. What about is happening in the grid cell with this discretization? Well, it's a kind of summary about every property that needs to be represented. Every grid block we will have porosity and net to gross in order to represent the power volume, permeability and net to gross in order to represent transmissibility, all fluid saturations. Okay? If we deal with components also, we eventually can add to this list the components, all fluids, pressures, and all relative permeability of all fluids. Okay? It's a summary. I'm just giving a big picture about what is the major characteristic of reservoir simulation. Okay, if you believe that the first part was heavy, be ready for even heavier stuff. Okay? We're going to work with some math. I try to be as simple as I can, but you need to, at least once in your life, face what is behind reservoir simulators. Okay? Okay. Flow equations for flows in porous media are based on a group of conservation equations, as I mentioned before. The conservation of mass, the conservation of momentum, and the conservation of energy. We are going to deal for simplicity with isothermal conditions, as is something that I also mentioned previously. Okay? However, we need to clarify that in certain cases, we need to deal with changes in the temperature also. And the equation will be, in the next slide, described for linear, one-dimensional case that can be extrapolated for more complicated situations, okay? Just, again, a big picture about what can be said on reservoir simulation. The idea is try to use the parabolic partial differential equation that represent conductivity. The equation that we are going to present here, which is a partial differential equation, is known like conductivity equation or heat. How do you mention heat equation? H-E-A-T. Heat equation, right? It's well known like heat equation, but it's also describing can be used for describing the pressure distribution in a reservoir. Even more, all well testing papers, theory developed is based on this heat equation, but instead of the heat of represented as a variable, what is represented as a variable is the pressure. Pressure as a function of space and time. Okay? This equation is derived from the continuity equation or Darcy's law in the simplest way. And we are going to deal with this equation, which is simple, in order to give us an idea about what is done in reservoir simulation. Okay? We're going to expose a case in one dimension, and as a simple way will be this heat equation representation of the pressure. We have here a bar, homogeneous material, and for simplicity we are considering that a fluid is flowing in one direction through this bar. At the beginning, supposedly the bar was is kept to constant pressure on both extremes. In the extreme x equals 0 and the extreme x equals L. However, in order to activate the process, remember, we have the same pressure in both extremes. If we have this both extreme with the same pressure, we are considering that nothing is happening yet. In order to activate the system, we are going to rise the pressure in one of the extremes, the extreme x equals 0. And let's see what happens. Okay? To the point, I'm not going to derive the equation directly, I'm going to expose what is the partial differential equation. The partial differential equation that is describing one phase fluid, assuming constant value for permeability, viscosity, and porosity, is given by that expression. Second partial derivative of P equal this factor in terms of porosity, permeability, compressibility, and viscosity times the first partial derivative of pressure with respect to time. This is the simplest one-dimensional heat equation. Okay? This equation, by the way, has analytical solution. Okay? We will see it. I will just put it there. In a course of partial differential equation, the way of solution, which is not difficult to follow, is explained. I won't omit explanation here. However, I am considering as a part of the assignment, final assignment. Question?
How much error, how much of an assumption is that constant viscosity and constant compressibility and changing pressure?
In my simple model, no. It's an ideal situation. But certainly, you will see that the uncertainty is in everything. When we do reservoir simulation, it's not only the just getting into that world, the equation has some simplification that need to be agreed in order to solve it. That introduces some error that you can make can be neglected if the time steps are small, or if your discretization or the cell is small. And there are ways of quantify that error according the size of your time steps and according the size of your cells dimension. You follow? There are ways. But again, these are simplifications. The numerical methods are solved, and not only because what I'm going to develop right now to expose in the next slide is how to deal with this derivative from the numerical point of view. And this is completely a part of the question that you take. We are assuming compressibility constant, permeability constant, etc., etc. There are papers that can expose you about this problem, but it's part of the people that do hard reservoir simulation. They go there. It's a topic. It's a serious topic. There are experts in this matter that spend years working not only like reservoir engineer, also like theoretical mathematician or theoretical physicists. Okay, let's continue. This equation is giving us pressure in terms of space and time. One case, one dimensional situation that we have, but we are changing, or we have variable in terms of the time of the space. If we didn't have changes on time, this part will be zero. And we can then simplify the situation to what is known the steady state description of the process. Okay, let me read it. The above equation implies both space and time dependence. I mentioned it can describe transient or time dependent flow. If the flow reaches a state where it's no longer time dependent, then the flow is qualified as steady state. That implies that this equals zero, or because it now, depending on one variable, this is the representation of the steady state. A steady state implies no transition in time. Steady state, no transition in time. Attention. What is the solution of this equation? Who can tell me? Integrate once. If you integrate once, what you get? First derivative equal to what? To constant. And if you integrate again, what you get? The function equal a constant times x plus another constant. So the single solution of this is the linear strike function, right? In fact, is what we have here. Let's try to understand the graphic. X is my horizontal axis. P, pressure, is in the vertical x. And what we have here is they are isolines. Isolines fixing the time t. T1, T2, T3, T4, T5. I am assuming that T1 is less than T2, T2 is less than T3, etc., etc. What is happening here? Remember that I rise the pressure in my string x equals 0 to T1. And then I can write how is the curve for time T1 for the first time. And the time is transient, is in transition, these curves are more and more pronounced. Remember that I am obligating my system keeping the pressure P0 in my string L. You follow me here? However, when the time tends to infinity, sooner or later, it's not going to depend anymore of the time. I'm going to the steady state solution. For some period of time, depending on properties of the system, the pressure change increase in the whole bar transient solution. However, for a very large period of time, the pressure tend to the steady state solution. Is what I said. Is what I said before. That's an analytical solution. You recognize it? Have you seen a course of partial equations? You see it? Do you have a course on partial equations or no?
Engineering math.
How do you zoom in and out?
It's optional or no?
No.
It's obligated?
Yeah, they're linear.
Yeah, it's
So you can take it like an elective.
Yeah, it's good.
You should have it.
You know?
Should have it. Okay. This is called a Fourier series.
What?
Fourier. Fourier. Fourier series. There are many individual solutions that when you add it, you give the whole solution of your equation. Just take a look to this term, the exponential term. Look this negative value here. When t tends to infinity, this whole exponential goes to 0. When you go to 0, then you get this solution, the linear solution. Okay? As I said before, I am considering probably part of the assignment, that you go to books and study the way that is solved this equation, but I haven't decided yet. But for changes, you are T. Okay, some comments. The previous slide is giving me an analytical solution, okay? And certainly some partial derivative equation can be found in our flow description that can be solved analytically if we make a lot of assumptions. However, if we do that, probably we won't be able to use it for representing what is happening in a reservoir. So because of that, we need to deal with some balance and provide and go to numerical solutions. Here, for illustration purposes, the linear flow equation above will be solved numerically with standard finite difference